Hey everyone, this is Nicole from Kenhub, and today we'll be taking a closer look at your internal plumbing. In other words, we'll be talking about the histology of arteries and veins. You will probably already be aware that the general function of blood vessels is to transport nutrients and waste products around the body to be processed in the right places. Arteries carry oxygenated blood away from the heart and to the body's cells, and veins carry deoxygenated blood back to the heart. Capillaries are the tiny vessels that permeate the body's tissues and deliver the blood within the range of all the cells that need it. Our tutorial today will familiarise us with the histological features of arteries and veins. Here we can see an artery on the left and a vein on the right. From first glance, we can see that there are differences between the two, and by the end of this tutorial, you'll be able not only to describe and see the general features of blood vessels, but also you'll be able to determine the distinguishing features that make an artery and a vein a vein. In this tutorial, we'll be looking at the layers of a blood vessel and the various components we find in these layers. From there, we'll look at the types of arteries, capillaries, and veins, and finish off with the clinical note, where we'll look at atherosclerosis. Without further ado, let's take a closer look at the layers of a blood vessel. To start us off, we're going to discuss the various layers and cell types that make up a blood vessel. Arteries and veins both differ in their structure slightly, as they're both adapted to accommodate different blood pressure levels. But the core elements, as we'll see in just a moment, are essentially the same. Our image here is a blood vessel cut lengthways. The blood vessel walls are at the top and at the bottom of the image, and directly between these two walls is the lumen of the blood vessel, and the lumen is the space where the blood travels through. We're going to be starting with the layer closest to the lumen and work our way to the outside of the blood vessel wall. Blood vessels have three layers that we should be familiar with, and as we go through these layers, we'll present the arterial version of the layer first, and then show how the venous layer compares to it. The first layer is the tunica intima. Here we have an image of the tunica intima of an artery, highlighted in green. This is the layer of the blood vessel closest to the lumen and blood, and it's made up of a single layer of endothelium, then subendothelium, and then the internal elastic membrane. Let's take a closer look at these. The endothelium of the blood vessel here is directly in contact with the lumen. This image on the left shows the endothelium of an artery, highlighted in green, and this image on the right shows the endothelium of a vein. No need to worry about the specific differences in the two here though, as these images are just examples. The endothelium is made up of numerous endothelial cells, highlighted individually here. The endothelial cells have a number of functions, including the absorption of nutrients and oxygen from the blood and the disposal of waste into the blood. In some areas of the body, like the brain, the endothelial cells are so tightly bound to their neighbour that they act as a barrier preventing the passage of any materials between the cells and into the surroundings. This is more commonly known as the blood-brain barrier. Just below the endothelium, we have the subendothelium, highlighted here in green. The subendothelium lies between the endothelium and the internal elastic membrane. It is a layer of connective tissue, and its main function is to support the endothelium. The internal elastic membrane is a single layer of elastic connective tissue that supports the above two layers. Elastic fibers appear as dark squiggly fibers. When viewed in a lot of histological images, this particular feature allows you to easily distinguish them from other fibers. The elasticity of these fibers allow for the blood vessels to adjust to the pressure of fluctuations in the blood, and the recoil of elastic fibers aid in the propulsion of blood through our vasculature. We will see elastic fibers in other layers of the blood vessels, and we'll also see their abundance in arteries rather than veins, which we'll explore a little bit later in the tutorial. Now that we've seen the layers found within the tunica intima, let's take this time to quickly compare this layer between a vein and an artery. The tunica intima of a vein is comparable to that of an artery, having the same layers that are relatively the same thickness. We can see it here highlighted in green. However, this layer does differ in that veins have valves, which are essentially folds of the tunica intima that protrude into the vessel's lumen. The valves cannot be seen in this image, so when looking at the two side by side like this, we can see that they're quite similar. Distinguishing an artery and a vein from one another is best done through examination of the shape of the vessel, as veins will be less structured and more collapsed than arteries, which appear more circular. The most discernible feature, however, is the middle layer of the blood vessel, the tunica media. The tunica media is the middle of the three layers within a blood vessel. The highlighted portion of this image is the tunica media of an artery. This particular layer consists of smooth muscle tissue, elastic fibers, and connective tissue to varying degrees depending on which artery we're looking at or what type of blood vessel we're viewing under the microscope. The smooth muscle tissue within blood vessels is under involuntary control by the sympathetic and parasympathetic nervous systems. In this image, we can see that the tunica media appears to be almost composed of multiple transverse layers stacked upon one another. An important feature to note within the tunica media are the elastic lamellae. The term lamellae just refers to layers of some kind of tissue. As we mentioned before, elastic fibers appear as darkly stained fibers and are highlighted in green in this image. Here's an unhighlighted one, just so we can see how darkly they stain in comparison to neighbouring tissue. We can also see that the elastic lamellae are separated from one another by layers of smooth muscle and connective tissue. The thickness of this layer and the amount of elastic fibers and smooth muscle does change drastically within our venous structures. When looking at the arterial and venous tunica media side by side, it is quite apparent how much they differ in size. A venous tunica media usually has more elastic fibers than smooth muscle, with the arterial tunica media having an abundance of smooth muscle as compared to its venous counterpart. Now, before we dive into the final layer of blood vessel, there's a layer that separates the tunica media from this outermost layer, known as the external elastic membrane. This layer is similar to its internal counterpart as it acts as a boundary between two layers. Also made of elastic tissue, the external elastic membrane acts as a boundary between the tunica media and the tunica externa, which is our next and final layer. The tunica externa is the outermost layer, or the layer farthest from the lumen, and is sometimes referred to as the tunica adventitia. This image on the left shows the tunica externa highlighted within an artery. It is primarily composed of connective tissue that supports the vessel and helps anchor it to surrounding structures. Taking a look at the venous tunica externa on the right, we can see that it is made up of similar connective tissue. The varying thickness of the tunica externa in both arterial and venous structures varies depending on the location and the size of the vessel that we're looking at. You cannot distinguish an artery or vein by just looking at the tunica externa. Now that we've discussed the general layers of blood vessels and how these layers differ between arteries and veins, we're going to dive into the various types of arteries and veins. Let's start with the different types of arteries. The first type of artery we'll look at are elastic arteries. On the image here, we can see a pinkish layer full of cells and different types of tissue. This is the tunica media of the artery. The main characteristics of elastic arteries are the vast number of collagen and elastic fibers that we find within the tunica media. This particular characteristic allows for the vessels to expand with blood and propel the blood through the circulation by recoil of the elastic fibers. The aorta and pulmonary arteries are examples of elastic arteries that propel large volumes of blood to the systemic and pulmonary circulation respectively. Elastic arteries generally propel blood towards muscular arteries that can either constrict or dilate, controlling the flow of blood to particular areas of the body. The mechanism by which this happens is a result of the vast number of smooth muscle cells that are found within the tunica media of these vessels. We can see right here the layers of smooth muscle cells that, when stimulated or not, can control the diameter of the vessel. Muscular arteries will then begin to feed blood into smaller vessels called arterioles. In the images here, we can see several arterioles highlighted in green. These vessels are much smaller than muscular and elastic arteries, and they are the final vessels blood travels through before it enters capillaries to dump nutrients and oxygen into the tissue. Arterioles have an endothelium and have a much smaller tunica media, usually consisting of only a couple of smooth muscle layers. Arterioles play a huge role in controlling vascular resistance. They can constrict, causing the diversion of large amounts of blood from particular areas of the body, or they can dilate and allow for more blood to flow through to whichever area of the body they may be in. From arterioles, blood then flows to the smallest of all blood vessels, the capillaries. Let's take a closer look at these now. Being some of the most important blood vessels in the body, capillaries are the smallest blood vessels that blood travels through. At these vessels, red blood cells travel through capillaries as if in a single file due to the small diameter of the vessels. This allows for nutrients and oxygen to leave red blood cells and enter tissue. It also allows red blood cells and blood to pick up carbon dioxide and waste materials for recycling or expulsion from the body. There are three types of capillaries that we'll look at here. First, let's start with continuous capillaries. As the name suggests, continuous capillaries contain no breaks or holes within their walls and continue as a tunnel for blood cells to travel through. The image here has highlighted a continuous capillary in green. This image has been taken from a section of lung tissue and shows a capillary found along the alveolar wall. If we take a closer look at this vessel, we can see some red blood cells located within the capillary. In this image, we can also appreciate how the capillary diameter is only wide enough to allow blood cells flow through the vessel one by one. Another important feature to note, but that can't be fully appreciated in this image, is that the endothelial cells of continuous capillaries are tightly bound by tight junctions where the neighboring cells touch. This completely contrasts with our next type of capillary, known as fenestrated capillaries. These type of capillaries allow for greater exchange of waste and nutrients between the blood and surrounding tissue. So we find fenestrated capillaries in areas that require quite a bit of exchange of materials between the blood and the surrounding environment. Fenestrated capillaries can be found in the kidney, endocrine glands, and the small intestine. Lastly, almost like an extreme case of fenestrated capillaries, we have discontinuous capillaries. We find discontinuous capillaries almost exclusively within the liver, and you can see them highlighted in green on the slide. Discontinuous capillaries act to release blood into a tissue, in this case, detoxifying liver, allowing the hepatocytes to eliminate toxins, receive nutrients, and remove wastes easily and efficiently. As blood passes through the capillaries, it eventually reaches the venous blood vessels. Let's take a look at the different types of veins now. Similar to how we just discussed the arteries from biggest to smallest, the blood leaving the capillaries will enter into the smallest type of veins, which eventually drain into larger and larger veins until the blood returns to the heart. The first of the two types of veins that we'll look at today are venules. Blood leaving the capillaries will enter into a system of venules, which are essentially the venous counterpart of arterioles. A characteristic feature of venules and veins in general, when looked under a microscope, is that they're generally thin-walled and irregularly shaped. You can see in both of these images that these venules do not take on an almost symmetrical circular shape like many arteries do. From venules, the blood then travels in medium veins. The most apparent thing that we notice when looking at the image on this next slide, as compared to the ones that we just previously saw, is that medium veins are larger than that of venules. They are still thin-walled and irregular in shape, and we can also see that these vessels contain an abundance of blood cells within their lumen right here. Medium veins then feed into or come together with other medium veins to form large veins like the superior and inferior vena cava. These large veins are similar in structure to medium veins, having irregular lumen shapes, but are characterized by a thick muscular tunica externa, which contains longitudinally arranged smooth muscle fibers. So that's all for our main arteries, capillaries, and veins. However, like all other tissues, larger and thicker blood vessels require some mechanism by which they can get nutrients and eliminate waste. This is accomplished by what is called the vasa vasorum, which we'll quickly look at now. In this image, you can see the vasa vasorum highlighted in green. These smaller blood vessels are actually found within the walls of larger blood vessels and act as their blood supply. Due to the thickness of these large blood vessels, nutrients and oxygen are unable to penetrate through and supply all of the layers in the blood vessel wall. Thus, the vasa vasorum is needed to mitigate this issue. That about wraps up our histology of blood vessels. Now let's touch on one important clinical topic that is useful to be aware of. Atherosclerosis is a condition affecting arteries. In a healthy artery, blood is able to flow through freely and unobstructed. However, atherosclerosis begins when lipids and cholesterol within the blood manage to get through and under the tunica intima of a blood vessel. Once under the tunica intima, the fats can oxidize and attract white blood cells and other cells within the blood and the wall of the blood vessel. The white blood cells acting on the fats releases several products that result in the buildup of a solid plaque in the blood vessel wall. As the plaque grows, it pushes the overlying tunica intima further into the lumen of the blood vessel, causing the lumen to become more narrow. On the left of this image, we can see the plaque protruding into the lumen of the artery. If the lumen of the blood vessel becomes too narrow, blood supply can be limited to whatever structure is being supplied by the occluded vessel. So if this occurs in the heart, cardiac tissue can die due to a lack of nourishment from blood, leading to a heart attack. Or if it occurs within an artery within the brain, the same can occur to neural tissue and cause a stroke. This brings us to the end of our tutorial. Now that we've reached the end, I'm going to give you a quick recap of what we covered today. Please feel free to use this as a checklist for your studies on the histology of arteries and veins. First, we started with the components of a blood vessel, touching upon the differences between some of these between arteries and veins. We covered the first layer of a blood vessel, the tunica intima, and its four components: endothelium, endothelial cells, the subendothelium, and the internal elastic membrane. Underneath the tunica intima, we found the tunica media, which contains elastic lamellae, and the external elastic membrane, which marks the beginning of the final layer of our blood vessel, known as the tunica externa. After we covered the components, we moved on to three types of arteries: elastic arteries, muscular arteries, and lastly, the smallest of the arteries, the arterioles. From the arterioles, we made our way to the three types of capillaries: continuous capillaries, fenestrated capillaries, imaged here on the slide, and discontinuous capillaries that are primarily found in the liver. Last but not least, we discussed the two types of veins, the smallest, venules, and medium veins. We also briefly touched upon the vasa vasorum that provide a blood supply for the larger blood vessels. And that wraps up our histology of the arteries and veins. Thanks for joining me.